This is SpaceTime Series 27, Episode 49, for broadcast on the 22nd of April 2024. Coming up on SpaceTime, discovery of the most massive stellar black hole in our galaxy, rewriting the evolution of white dwarf stars, and development of a new, bigger Cygnus cargo ship. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Astronomers have identified the most massive stellar black hole yet discovered in the Milky Way galaxy. The black hole was spotted in data from the European Space Agency's Gaia mission because it imposes an odd wobbling motion on the companion star orbiting with it. Follow-up data from the European Southern Observatory's Very Large Telescope in Chile, as well as other ground-based observatories, were then used to verify the mass of the black hole, putting it at an impressive 33 times the mass of our Sun. The black hole, which has been catalogued as Gaia BH3, is located just 2,000 light-years away in the constellation Aquila the Eagle, and that makes BH3 the second nearest stellar mass black hole to the Earth, the nearest being Gaia BH1, which is some 1,560 light-years away in the direction of the constellation Ophiuchus, the Serpent Bearer. BH1 has some 9.62 times the mass of the Sun, less than a third that of BH3. Stellar mass black holes are formed from the collapse of massive stars, and the ones previously identified in our Milky Way galaxy are on average around 10 times as massive as the Sun. Even the next most massive stellar mass black hole in our galaxy, Cygnus X1, only reaches 21 solar masses, making the new 33 solar mass observation quite exceptional. Of course, it's not the most massive black hole in our galaxy. That title belongs to Sagittarius A star, the supermassive black hole at the galaxy's centre, located 27,000 light-years away and which has about 4.3 million times the mass of the Sun. But Gaia BH3 is the biggest stellar mass black hole known in the galaxy. Astronomers have found comparable black holes to BH3 outside our galaxy, and they've theorised that these may be formed from the collapse of stars which have very few elements heavier than hydrogen and helium in their chemical composition. Remember, any element other than hydrogen and helium, the elements created in the Big Bang 13.82 billion years ago, are considered metals in astronomy. And it's thought these so-called metal-poor stars lose less mass over their lifetimes and hence have more material left over to produce high-mass black holes after their deaths. But evidence directly linking metal-poor stars to high-mass black holes has been lacking until now. The study's lead author, Pasquale Panuzza from the Paris Observatory, says stars in binary systems tend to have similar compositions, meaning that BH3's companion holds important clues about the star that collapsed to form this exceptional black hole. And spectroscopic data has shown that the companion star is also very metal-poor, indicating that the star that collapsed to form BH3 was likely also metal-poor, just as predicted. Needless to say, further observations of this system will reveal more about its history and about the black hole itself. And of course, we'll keep you informed. This is SpaceTime. Still to come, rewriting the evolution of white dwarf stars and development of a new, bigger Cygnus cargo ship. All that and more still to come on SpaceTime. Well, as mentioned a few weeks ago, astronomers have discovered a small population of white dwarf stars that have mysteriously stopped cooling. The findings, reported in the journal Nature, are based on data from the European Space Agency's Gaia spacecraft, which identified the population of white dwarf stars that apparently ceased cooling more than 8 billion years ago. What that means is that somehow these dead stars are generating energy, and astronomers aren't totally sure how that can happen. The findings have important implications because they're forcing astronomers to change the way they determine the age of stars. See, up until now, the cooler the white dwarf, the older it's always been assumed to be. But following these new discoveries, that no longer holds true. White dwarfs are the collapsed cores of Sun-like stars. Stars shine by fusing hydrogen into helium in their cores. That creates hydrostatic equilibrium. In other words, energy of the hydrogen fusing counteracts the crushing effect of gravity, keeping the star in balance. But when they run out of core hydrogen to fuse, that balancing act ends and the star starts to crush down on itself. Now, as the stellar core contracts, it's also increasing core temperature and pressure. Eventually, it reaches a point where it's hot enough and there's enough pressure for fusion to recommence, with the helium that it's created fusing into carbon and oxygen. At the same time, a shell of hydrogen outside the core is now also hot enough to begin burning. And that causes the star's outer gaseous envelope to expand outwards. And as the gaseous envelope's surface is now further away from the contracted core, it starts to cool down, and the star turns into what we call a red giant. Of course, eventually the star will also run out of helium to fuse in its core, and as it's not massive enough to fuse heavier elements, that's when the star dies. Its bloated outer envelope will float away as a spectacular cloud known as a planetary nebula, exposing its white-hot stellar core, which astronomers call a white dwarf. These stellar cores are then left to slowly cool over the eons. Astronomers think about 97% of all stars will become white dwarfs. Scientists have long considered these stars stop producing heat and cool down until the dense plasma in their interiors freezes into a solid state and the star solidifies literally from the inside out, becoming a black dwarf. Now, that cooling process can take billions and billions of years. In fact, astronomers don't believe any white dwarf has cooled down enough to become a black dwarf yet, at least not in the 13.8 billion years of the universe's existence. And that's where a new theory designed to explain the Gaia observations comes in. Now, according to this new theory, dense plasma in some white dwarfs doesn't freeze gradually from the inside out, but instead forms less dense solid crystals, which, being lighter, tend to float upwards, displacing the denser plasma, which sinks downwards towards the centre. Now, the authors believe the transport of the heavier material towards the centre of the star releases gravitational energy, interrupting the star's cooling process. They hypothesize that this happens in some white dwarfs but not others because of differences in the composition of the star. One of the study's authors, Simon Bluin from the University of Victoria in British Columbia, says that some white dwarf stars are formed by the merger of two different stars. He says that when these stars collide to form a new white dwarf, it changes the composition of a star in a way that allows the floating crystals to develop.
White dwarfs are dead stars, and so they're stars that have run out of fuel. They don't have anything left to burn, and so the expectation is that they should cool down for the rest of time. So it's really like to describe this as a campfire that you just abandon. With time it will just cool down. Now, the big surprise is that a few years ago, there's this population of white dwarfs that was discovered that basically stopped cooling for billions and billions of years. And so that's as surprising as abandoning your campfire and coming back a month later and seeing that the embers are still quite hot. And so our recent work finally found the explanation for why those white dwarfs can keep shining as bright as they do, even though they don't have anything left to burn.
Considering you're looking at this population of white dwarfs on a human timescale, how do you know they've stopped cooling down?
Yeah, that's an excellent question. So because they cool down over timescales of billions of years, we cannot see this cooling live. Like if I observe a white dwarf now and I observe it next year or in 10 years, it will look pretty much the same. So the way we see that is more statistically. So the idea, so let's say you're on a plane and you see a long road and you see that on the left end of the road, there's not that many cars, and on the right end of the road, there's also not many cars, but somewhere in the middle, there are many cars that are there. So from the plane, you cannot see how fast the cars are moving, but if there are many cars at some specific locations on the road, you can conclude that they're probably moving much more slower in that region. So that's why they all accumulate there and forming a traffic jam. So it's really the same idea with our white dwarfs. So if we place them along a temperature scale, we see that there's a specific temperature where we have many more white dwarfs than we expect. So at higher temperatures, when they're young, we have not that many. And at cooler temperatures, when they're older, there's not that many. But in between, we see this big bump in the number of white dwarfs. dwarfs. So the only way we can explain that is if they cool down much more slowly. They essentially stop cooling for billions of years, and so they all accumulate at this specific temperature.
And what do you think is causing that?
So what we think is causing that, as the white dwarf cools down, at some point it is cool enough that the interior freezes into a solid state. So the interior of a star is made of a plasma, and often we have this picture that a plasma is a fluid thing, but actually a plasma can also be solid. So being in the plasma state only means that you have removed the electrons from the atom, so you only have bare ions and electrons. So when the white dwarf becomes cold enough, it freezes. We call this white dwarf crystallization. And the classical picture is that this freezing process starts at the very center of the star. The reason for that is simply that this is where the density is highest, so that favors the solid phase. And so you have a crystal forming at the center of the star, and it gradually grows. And so the star freezes from the inside out, and that's a process that takes a few billions of years. Now, what we found is that for some specific white dwarf compositions, the crystal that is formed, instead of being denser than the liquid phase, it is lighter than the liquid phase. So it wants to float up. And that's, of course, the same thing as ice cubes floating in a glass of water.
Yeah.
So you cannot put ice cubes at the bottom of your glass. They will always want to float up. So the same thing is happening here. So you start forming crystal at the center, but they cannot stay there because they are buoyant. So they will rise up. Now, by rising up, they will displace liquid down because you need to fill back the hole that's left behind by your rising crystal. And by definition, the liquid that's filling back this hole is more dense because the crystal is less dense than the liquid. And so you have this kind of conveyor belt of rising crystals and liquid going down, and gradually that pushes the more heavy material to the center of the star. And when you take things that is heavy and you put it at the center of a gravitational energy well, such as a star, well, you release gravitational energy. And so it is this release of gravitational energy that is stopping the white dwarf from cooling, because this is extra energy that it needs to get rid of in order to continue cooling down. And that takes some time. So it's really like a little heat engine that's keeping the white dwarf shining for an additional 10 billion years or so, even though it doesn't have anything left to burn.
Now, the implications of this, of course, are that you've just saddened a lot of scientists because you've prevented them from being able to use white dwarfs as time gauges.
Yeah, exactly. So that's probably the most important implication. So usually we use white dwarf as cosmic clocks. The idea is that the cooler they are, the older they are, and so we can measure the surface temperatures of white dwarfs and from that infer their ages. But now that this really complicates the picture because it's not obvious which white dwarfs had this additional cooling delay in their history and which one did not have it. And so that introduces a large uncertainty on the ages of white dwarfs. Now, of course, we suspect, so this very large cooling delay, for now, we only have evidence for it for a small fraction of known white dwarfs. So those are mostly very massive white dwarfs, close to the maximum mass that a white dwarf can have. But we suspect that there's also a similar thing going on for more standard normal mass white dwarfs. But this is not something that we can conclusively see from the observations at the moment. But that's kind of the logical follow-up from this research.
So we're talking about white dwarfs that are getting close to the Chandrasekhar limit.
Exactly, yeah. So the white dwarfs we're talking about are more than 1.05 solar mass and all the way to around 1.3 solar mass. Yeah.
Are all white dwarfs composed of the same materials, or can white dwarfs get massive enough to fuse more heavy elements together?
Yeah, good question. So most white dwarfs have a carbon-oxygen core, and so that's what you get after burning helium. Now, some of the most massive white dwarfs will instead have an oxygen-neon core. So in their history, they've become hot enough to fuse carbon. And it's actually an interesting puzzle because the white dwarfs with an oxygen-neon core, we think these are the most massive white dwarfs, above 1.05 solar mass or so. But to explain this extra cooling delay that's seen in the observations, we actually need those very massive white dwarfs to have a carbon-oxygen core instead of an oxygen-neon core. And that's not what's classically predicted by stellar evolution theory. But we think what's going on is that those stars are actually not the product of a standard single star stellar evolution, and instead they are the product of a stellar merger. So there are different types of mergers, like two white dwarfs merging together to form a bigger white dwarf, or a white dwarf with a subgiant star. So there are many different ways to arrive at the white dwarf phase, and we suspect that those very massive white dwarfs that have carbon-oxygen core probably, in large part, they come from a channel where you merge a white dwarf with a subgiant star. So the models that we have of those mergers, they do predict carbon-oxygen composition even at very high mass. So it just doesn't become hot enough basically during those mergers to fuse the carbon to make an oxygen core.
Are you going to look for more of these populations? Is that the plan?
Yeah, so what we are looking for right now is signature of this similar process for the more normal white dwarfs, which have masses around 0.6 solar mass, and they form the bulk of the white dwarf population. So we know they don't have this delay of many, many billions of years because we would already have seen it, but it's possible that there's an additional delay of the order of 1 billion years that is currently not included in our models, and so that affects the ages that we find for white dwarfs. So one of the things that I'm doing with different collaborators is to try to find whether we could see this delay by looking at binary white dwarfs, so systems where you have two white dwarfs that are far enough apart that they could not have interacted together, but we know they have the same age. And then the idea is that you find systems where one of the two white dwarfs is crystallized and one is not crystallized. And if you find a systematic discrepancy between their ages, well, then you know that there's something missing in the model. So that's what we're trying to do right now.
That's Simon Bluin from the University of Victoria in British Columbia. And this is Space Time. Still to come, development of a new bigger Cygnus cargo ship for NASA's supply runs to the International Space Station. And later in the science report, the Bureau of Meteorology has formally declared the El Niño weather pattern of 2023-24 has finally ended. All that and more still to come on Space Time. Engineers are developing a new updated version of the Cygnus cargo ship for future NASA supply missions to the International Space Station. First introduced back in the early 2000s, the Cygnus were initially designed to transport 2,750 kilograms of supplies in an 18 cubic meter pressurized cargo module built by Thales Alenia Space, mated to a service module built by Northrop Grumman. They were used to carry everything from food and water, spare parts, scientific equipment and other vital supplies to the orbiting outpost on missions twice a year. Now, over the years, as the Antares rocket which launches Cygnus has improved, Cygnus has also improved its payload capacity, now carrying some 3,750 kilograms of cargo in a pressurized module with a volume of some 27 cubic meters. This new version will be used for the NG-21 mission, which is slated for delivery to Northrop Grumman next month. Meanwhile, work's now underway on the NG-22. However, Thales Alenia Space have just announced that they've completed the primary structure of an even larger expanded version of the Cygnus. This one will have some 36 cubic meters of payload space, twice that of the original, and will have capacity for up to 5 tons of cargo, again, almost twice that of the original. The new spacecraft slated for its initial pressure test to confirm structural integrity in September, and it should be flying to the orbiting outpost next year. Unlike the SpaceX Dragon cargo ships, which are capable of atmospheric re-entry and are reusable, the Cygnus are designed for single use only, and they burn up in the atmosphere during re-entry. Cygnus, together with the Dragon, form the basis of NASA's commercial resupply program to the orbiting outpost. And they'll be joined later this year by a third player, Sierra Space, which will be flying a cargo version of their Dream Chaser wing spaceplane, together with its attached Shooting Star cargo module to the International Space Station from June this year. And like the Dragon, Dream Chaser is designed for atmospheric re-entry and will be reusable. Also, like the Dragon, Dream Chaser has been designed for eventual manned spaceflight. And that will give NASA a third option for low Earth orbit. This is Space Time. And time now to take a brief look at some of the other stories making news in science this week with the Science Report. The Bureau of Meteorology has declared that the El Niño weather event of 2023-24 has finally ended, with Pacific Ocean surface temperatures returning to neutral conditions. The Weather Bureau says there's now a growing likelihood that El Niño's cooler, wetter counterpart La Niña could return by September. The El Niño Southern Oscillation Index, or ENSO, normally brings hotter, drier conditions to eastern Australia as warmer water temperatures dominate the western tropical Pacific. The Bureau says global sea surface temperatures have now been the warmest on record for each month of the past year, April 2023 through to March 2024. And April 2024 is on track to be warmer than April 2023. La Niña is associated with wetter than usual weather conditions for northern and eastern Australia. That happens as cooler ocean surface temperatures dominate the western Pacific, strengthening easterly equatorial winds and shifting rainfall patterns towards Australia and Southeast Asia. Statistics indicate Australia usually experiences more cyclones during La Niña years. The El Niño, which lasted 7 months, followed back-to-back La Niña events. Now, if another La Niña does start up later this year, it will be the fourth such event in the past 5 years. The Bureau's prediction of a new La Niña event follows similar forecasts by America's National Oceanographic and Atmospheric Administration, NOAA, which says there's an 85% chance of a new La Niña event kicking off later this year. A new study has found that drinking more than 1 glass of sugar or artificially sweetened drinks per day could increase your risk of developing chronic kidney disease. The findings, reported in the Journal of the American Medical Association, are based on an international study of over 120,000 people. The study found those who drank more than 1 beverage a day increased their risk of developing kidney disease over 10 years. The authors say switching just 1 serve of these drinks over to a natural juice or water could help reduce the risk of incident chronic kidney disease. Scientists have unearthed what may be the largest marine reptile ever described. Fossils of Ichthyotitan sevemensis indicate the reptile was an estimated 25 metres long. Paleontologists found and pieced together fragments of an ichthyosaur jawbone discovered in the UK, noting that it was similar in size and shape to another found a few kilometres away. A report in the journal PLAS ONE claims the 2 jawbones probably belonged to a previously unknown species of ichthyosaur, a group of large ocean-dwelling reptiles from the age of the dinosaurs that looked a lot like today's dolphins. The length of the jawbones was used to estimate the size of this creature, although the authors caution that more evidence is needed in order to conclusively figure out just how massive it was. Ichthyosaurs first evolved around 250 million years ago, reaching huge sizes around 200 million years ago. But the giants didn't last long. They died out not long after evolving, although smaller ichthyosaurs continue to survive for millions of years. Well, it seems true believers in the paranormal are claiming a huge archival collection of newspaper clippings, books and assorted paranormal material, including first-hand reports of people who claim to have visited other planets, is positive proof of the existence of the supernatural. Actually, it's just evidence of the huge amounts of unproven claims to the paranormal that have been gathered over many years. Tim Mendham from Australian Skeptics says the extensive archive was gathered by Sweden's skeptical movement, and it's simply untrue for those who believe in the paranormal to claim it as proof.
There's this group of people in Sweden who have developed a physical archive, so it's a real big thing because everyone keeps making a big thing about how many kilometres of shelves with information which is documentation, anecdotal references, photos, you name it, on a whole range of paranormal phenomena. It's called the Archives for the Unexplained, and it's the world's biggest library of paranormal phenomena. And it is the work of a few people, some of whom are associated with the Swedish skeptics. Now, it's been picked up as if all this stuff, by having all this stuff, it means that the things they're covering is real. And the people who build it say, no, they haven't actually specifically said that, but what they're saying is they're building a depository of knowledge, and they say they are not judging it true or false. All they're doing is collecting. It's a library, right?
Because you have 1,000 documents that are 1% possible and 99% garbage doesn't mean that you've got positive proof. It just means you've got 1,000 documents that are 99% garbage.
Yeah, this is what I call the point scoring system. If you get one bit of proof which scores 2 out of 10 on the reliability scale, 5 of 2 out of 10 does not make a 10 out of 10. It makes 5 2 out of 10. And
yeah.
you're no better off. In fact, you're worse off because you're not getting any closer to definitive proof.
It's proving the fact that it's not real. Or unlikely.
These same stories refer to the fact that NASA has investigated UFOs. Fair enough. They've investigated UFOs and they found nothing there. But the fact that they've investigated doesn't mean they're there. That doesn't mean it's an actual endorsement of this UFO or UAP phenomenon. All they're doing is looking at it the same way the Pentagon looked at films, which were easily debunked actually, but they weren't good enough to point that out. And they said, yes, there are things out there which are unexplained. And people say, right, unexplained means alien tech. Or in some cases, ghosts we're talking about here. We're talking about a whole range of paranormal phenomena that these people have been looking at. And to me, they're doing the right thing. And as they say themselves, the archives say something is unexplained. That means we shouldn't reject it. We should investigate it. We should be open. And that's fine. That's what skeptics do. That's what scientists should do. There are some things you reach a certain stage with. I've heard this a lot of times, and it breaks so many laws of physics or whatever that I think it's unlikely that this is ever going to be true. So just investigating it or collecting info is not an endorsement that it is true. But anyway, these news stories have been picking us up. It's fascinating. It's got 4 kilometres of shells, so naturally it's very important. So here we have it. Something worthwhile being picked up and made to be something bigger than it really is.
That's Tim Mindham from Australian Skeptics. And that's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favourite podcast download provider, and from spacetimewithstuartgary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details. And if you want more SpaceTime, please check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as heaps of images, news stories, loads of videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram, through our SpaceTime YouTube channel, and on Facebook, just go to facebook.com/SpaceTime with Stuart Gary.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.